work in some eigenbasis of B? Can't I choose directions in n-dimensional Grassmann space, which after all I can take linear combinations of Grassmann vectors? Why don't I choose the directions so that I'm just living in the, I do the, I do a similarity transformation to put myself in that direction. In that case, the matrix will become diagonal in that basis, and then the exponential of the sum will be the sum of the product of exponentials, and we'll just get many things of this form, and there'll be a B for every eigenvalue of that matrix B, and the product of eigenvalues is known as the determinant, right? So we are expecting that the answer is equal to the determinant of B. But heck, it's cute to see and useful, not in this class, but in general it's useful to see the proof and how the Grassmann thing does it. It does it very similarly to the sort of the way that you end up with the Jacobian when you change variables in an integration measure. When you change from integrating in terms of x to integrating in terms of x prime, and you get a Jacobian factor, which is a square root of a determinant. No, it's a determinant, sorry. It's a determinant. Of course, that's the beautiful thing that these different exterior forms, the algebra of exterior forms, does for you. I'm about to replay exactly the same moral lesson here. Not just moral, I mean technically exactly the same thing is about to happen. But anyway, here it is. That's just, here's the proof. So the integral here. The integral is over all these d theta 1 stars to d theta star n, d theta 1 to d theta n, and so you can see how this is going to work. Hopefully it's obvious. I have 2n integrals. I'm not going to get any non-zero answer unless I expand this to nth order in the exponent. Okay? Otherwise I'll just get zeros by the axioms of Grassmann integration. I have to do nth order here, so I get 2n thetas. Sorry, n thetas and n theta stars, which then even have a chance of having a non-zero integral. So this, however, is 1 minus, so it's the exponential of the sum is the product of the exponentials. So let's just look at one possible choice of I and j and that exponential. I'll just Taylor expand it. It's 1 minus theta I star bij theta j. That's the entire Taylor expansion for that one term. Okay. So what I'm telling you is I have to choose out of this product over I and j, I have to choose if a typical term here is you take some number of 1s and some number of theta squareds. That's the typical term in expanding this product. I have to choose a total of n of these, and the rest are 1s. You see, there are n squared terms. So I have to choose n of these to be these, or thetas, theta squareds. that is equal to so integral d theta 1 star, integral d theta n, and so here it is, sum over permutations I. We'll see what I mean in a second. Oh gosh, I've used the word I. A. P. P. Okay, now you'll see what I mean here. Where I choose -1 to the P, and I have so let me start at this end and write theta 1, B 1, P 1, theta P 1. Okay, so first, I know for sure that in the theta terms that I keep, I know that theta 1 is going to appear. In fact, it appears just once. Any more and it'd be dead. Any less and I'd be dead. Okay? So let me write that term. There it is, theta 1. But if I'm choosing something with theta 1, I don't know which Bij. I know that it's a B1. Okay? I know it's something 1. Who is the something? Well, I'm saying it's some permutation. It's something drawn from all the other indices that I have. It better not be 1. Well, that would give me theta 1 squared. So you can see the reason that permutations are coming around is because you have to have chosen, in this whole list of theta squared terms that you're going to write down, n of them, if I think in terms of the theta, and I say there's theta 1, I know I have to see theta 1, I have to see theta 2, I have to see theta 3, I have to see theta n. But which starred theta they're matched with, okay, in the sense of this. Which starred guy they're matched with must be a permutation of 1 to n. Okay? Because there can be no repeats. So the most general way you can pick, you're doing all these different possibilities. You choose a 1 or you choose this. The most general thing is of this form. Let me write it, and then I hope it is theta n b p n where the permutation I'm calling the permutation in the abstract p, and p sub 1 is, say, 7. Okay? It's the permutations of the numbers 1 to n are called p1 to pn. Okay, now, question.
Yeah, I guess you would do immediately after this, but if you do the similarity transformation first, so you diagonalize, then you don't have to worry about the permutation, because anyway you just have like...
Yeah, if you go to the I'll use Peskin's word. I invite you to do the diagonal approach, which is very useful in general. I mean, there are a lot of very brilliant formal manipulations of this object, and then you avoid doing all this horrible mess. I'm doing the horrible mess because I'm trying to show you how it robotically calculates the determinant. If you've ever written a determinant out for a matrix of Mij, what is the determinant of this? In terms of actual components, it is not a pleasant sight. Usually we talk about how you calculate the determinants by giving the algorithm. Calculate the determinant by calculating this other subdeterminant and blah, blah, blah. Nobody wants to see the whole thing. And you might think, how does it know to give that horrible formula? And I'm just saying, it is vaguely useful in some contexts to just see how it does it. Without the ultra-slick notion of just diagonalizing it, turning it to a bunch of one-dimensional integrals, and boom, you're done.
Is that -1 to the p or -1 to the n?
Yes. So it was supposed to be, according to my notes, not that I trust them, it was -1 to the n. But let me just think it out here. Oh, right. It's obvious. -1 to the n. Good.
And then your first matrix B, it's B sub p and n.
Yes. So then, this is equal to sum over permutations, integral integral of all of this junk, the -1 to the n. Then there's theta n star down to theta 1 star and theta. Sorry, I should say Pn star P1. Theta n down to theta 1, and then this B Pn n down to B P1 1. And so let me take all of these theta stars and move them to where the theta star integrals are being done. So I can use the axiom for integration. Right now, they're the theta integrals between my theta star and my theta star measure. Well, if it's a C number, just push it through. If it's odd, then you pick up a -1. That's exactly what this -1 to the n is, right? If this is a product of n Grassmann numbers, if n is even, then this would just be 1. So in that sense, I can just drop the -1 and just write integral d theta star 1 to d theta star n and theta star Pn down to theta star P1. And then the integral d theta 1 to d theta n down to theta 1, and then this b P1 n b P BP1. And I'm now writing over myself. What is this? If only they were ordered, it would just be 1. But they're not ordered. There's a permutation, and every turn, every exchange is costing me a -1 by the Fermi statistics. So this is in fact got a name. The thing that's totally antisymmetric copies of plus and -1 is just P n dot 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 P. This is just the epsilon tensor in n-dimensional space. Okay? Why? Because it's plus or -1 depending on whether to order these from 1 to n. I have to make n an even number of permutations or exchanges or an odd number. Okay? Because if I ordered them 1 to n, then this would just be 1. Okay? So this is inequality. Okay? And then this is just the way I've chosen to order it. This is just 1. Sum over permutations, products of matrix elements in this sense, with this epsilon. This is determinant. That is that messy formula for the determinant enough of this. This will be, this result, derivation is, I'm just saying that this way of doing it gets you what you would call the least processing derivation of determinant. The idea that the determinant is the product of the eigenvalues, that's a very deep fact. Maybe it's not too hard to derive, but it's a very deep fact. And this derivation does not make use of that deep fact. It's bulldozer. It gives you the determinant. Okay. Fine. What do we need? I think I want to do one more example. I think this determinant structure is crucial for some things that we're going to do later when we're doing gauge theory. But I think for the moment we don't need this. We need to know how to complete the square. In other words, we need a kind of, quote, source term. Right now there's nothing to care about in this result. Okay. So let's do that. And so we're going to do an integral which looks like d theta 1 star d theta star n d theta 1 d theta n e to the minus theta dagger b theta, where b is a standard matrix in n dimensions. And then let's do eta dagger theta plus theta dagger eta, where eta is also a G number, in quotes, source. Of course, we're not even doing field theory yet, but we know that that is what's coming, so let me just call it, in quotes, a source. How do we do integrals of this type? If all I really care, I don't care about overall proportionalities, I care about the eta dependence, which is the source dependence. That's, if you recall, where we're headed by analogy with the scalar case. This whole thing is equal to e to the minus theta dagger plus b inverse in the matrix sense. I hope this is right. Let's see. Theta plus b inverse theta. So, of course, I'm not finished because there's always that extra completing the square part to it that you have to subtract off. But first, this gives this term. Oh, there's a minus, I guess, here. So I get eta dagger theta from these two terms, and then the other one I would get theta dagger. Again, the minuses canceled. Theta dagger eta. Okay, and so to write an equality, I should add eta dagger b inverse eta. And by shifting integration variables, by that beautiful property that we axiomatized, we didn't derive it, we just said, I want it, where this is theta and this is theta prime, right? By shifting to those variables and the shift invariance of these integrals, this is, well, here I'll write it as an equality since I can, with this result up my sleeve. It's determinant of b times a factor e to the minus thing, which is not being integrated. For a while, this is going to be a proportionality constant independent of eta. So I won't really care about this. This is just being kept in reserve for later. So the answer that we cared about is simply that this structure, which should remind you a lot of the Gaussian integral results that we had for scalars. J, some sort of inverse of whatever the quadratic term was, eta of J. Okay, that's what it should remind you of. But these are Grassmann numbers, so that'll change things a little bit. Okay, so very nice. This is the most general Gaussian integral that we'll ever have to do in perturbation theory, except that I'm not doing fields. I've just done n of them. Now we're going to try and take this n to be as large as space-time, the number of points in space-time, right? We're going to fields. All of this is incredibly easy stuff, except figuring out which dimensionality of space you're talking about, depending on whether you're in the analogy or not the analogy. I mean, there's a lot of packed analogies here, sounding very similar to the real thing. So it just requires just making it a little bit familiar. Okay, so Dirac fermion. Path integral, of course. We are going to take, we're not going to start with the result and insert complete sets of states and all of that motivational stuff that I did in the scalar case. I'm going to tell you the answer and then prove that it's correct. Okay? So first, you just get told it. So first, the Dirac field is a G-number field. It's a function of ordinary C-number space-time, but the value of the field at that point in space-time is a G-number. Psi at the North Pole anti-commutes with psi at the South Pole. And the psi bars both of these are crucially psi and psi bar anti-commute with no h bar, delta function, nothing. Because these are the things in the path integral. The path integral was supposed to put the h bar into physics. But before you do the path integral, the field that is being path integrated doesn't have any sort of weird h bar. So these are G number fields. They anti-commute. They all anti-commute. There's no leftover remainder term. To be robotically correct, I should put the spinor index. In other words, yes, there's going to be matrix structure of a different type, the Dirac type, but each component of the Dirac field is a C. Again, probably only if you remember that I use Dirac matrices as sort of toy models of Grassmann numbers. But I know one. We've axiomatized Grassmann numbers. There's no connection. Okay, so e to the I w eta is defined as the integral d psi bar d psi, which really means a product over every point in space-time. You know that. It also means a product, I won't keep writing it, but it means a product over Dirac indices. It's a 4-component thing, so obviously each of the components is pretty nobody ever writes this. We're going to write the sort of the baseline thing, which is integral d4x psi bar I d slash minus m psi. This is the Dirac action. I presume you saw it in your first course in quantum field theory or advanced quantum mechanics or something. So that's the Dirac action. That's the base. So this is what you would guess. A path integral of e to the I action. Okay? This is the Dirac last time, I'm using the bar to sneak in an extra gamma 0 just for convention's sake, because for all the reasons that we do use the bar rather than dagger. Okay. So in detail, it's got a gamma 0 there. This is daggered, and the dagger means that you're doing a sum over components and so on. Okay, well, immediately you see that other than the fact that the number of space-time points is infinite, which we don't absolutely know because nobody's gone down to arbitrarily short distances to see whether we live on a lattice or not. So that's an ultraviolet question. So other than ultraviolet issues, which we are yet to sort of completely tackle, this looks exactly like this. So I can just spit out the answer, okay? I don't even care what the determinant of this Dirac matrix is, although there are many interesting problems where you do care.